Now we have Barry Sanders from the University of Calgary. I'll introduce you more formally to other people ahead of your colloquium. But for now, we have Barry Sanders, who's going to tell us about harvesting entanglement from the vacuum requires synchronization. And it is going to be a Blackboard talk, and he's encouraged you to ask lots of questions and have lots of interaction.
Pleasure to be here. It's my third time in Bangalore, so I feel like I'm an expert on the place. So if anybody needs to know what to do and where to go, let me know. So what I want to talk to you about today is, okay, let me tell you the story. So when I was asked to come, it was for the colloquium tomorrow, and I saw the title was Entanglement from Gravity, and I just happened to be working on something like that. And then it's a discussion meeting, whatever that means. And so I interpret a discussion meeting doesn't mean I actually have to really know what I'm talking about or have a result. So what I'm going to tell you about is kind of unfinished. I've been working on it until 2 minutes ago. And so I'll tell you where we're at, what the problem is, where we're at, and then if anybody wants to ask questions, great. And if you can see an answer where I'm stuck, that's fine too. But I'm taking literally the discussion meeting concept. And my background is I'm more of a quantum information, quantum mechanics, quantum optics kind of guy, so I'm not so used to thinking about gravity and that kind of thing. But lately I've been doing it. I went to a workshop a year or two ago, and there was people there who were talking about Benny Resnick. If anybody knows Benny Resnick, had this idea about a decade ago that the universe has some ground state. You know, you write the quantum field for the universe, there's a ground state, and the ground state has long-range entanglement. And so the concept is that somehow two parties, I'll call them Alice and Bob could have their detectors at two different points of the universe, and in principle be able to extract entanglement from that. And for somebody from my background, I'm trying to figure out, like in a quantum information kind of way, I'm thinking about, okay, it might be possible in principle, but will the entanglement break down somehow exponentially or Gaussian or polynomially with separation? The kinds of things that we worry about is not, is it possible in principle with some small amount, but we care about things like, how do these kinds of effects scale? And then I eventually harangued Eduardo Martinez. So Eduardo Martinez, he works at Perimeter Institute, University of Waterloo. So after talking to a number of people, he was the one who couldn't get away when I grab him and hold on to him and say, look, I really want to understand this. And so Eduardo and I have been working through the calculations, and it's kind of boring in a sense because it's taking the concept and then trying to write down very carefully what the steps are, what the resources are. Do Alice and Bob need a clock to be able to figure out how much entanglement to harvest? And the question is, for me, what is the, if they're going to somehow extract the entanglement from the vacuum, what are the corresponding timescales? And I think we have an answer to that, so I'll give it to you at the end if I get that far. Otherwise, you don't hear the ending. Okay, so the idea here, as you've seen, the talk is entanglement harvesting requires synchronization. So then the idea is somehow, this is my simple concept of the universe. So the universe is like a box, and it's got a field, and the field has a ground state, and there's Alice, and there's Bob, and somehow they have to do a protocol where they're going to work together to have, each one will have a detector. I'll use an Unruh DeWitt detector here, and so they each have an Unruh DeWitt detector, and those detectors are going to interact, they're going to be turned on, interact with the universe, background, the state of the universe, turn them back off, and then Alice is going to hop on a rocket, fly over to Bob, and then they're going to do a measurement to find out if they've got entanglement. You get the idea? So the way I'm thinking about it is not if you calculate the ground state of the universe, is there entanglement, but what do two parties need to do to actually perform that test? And this emerges out of the work of Resnick. So Resnick had a paper in Foundations of Physics. I think it was somebody's birthday. Bekenstein. So about 10 years ago, there was a special issue of Foundations of Physics, and his gift to Bekenstein at the time was to conceive of this. So this idea, I think, comes out of Resnick, and then he and collaborators wrote more careful papers about it. So I'll explain their idea, and then we'll see how to deal with that. Okay, so the first thing is we have Unruh DeWitt detectors. Okay, and these kinds of detectors, I'll just write down the field operator, so this becomes important. So there's the field operator for the universe. It's got space and time dependent quantities. I'm going to deal with space and time separately here. And then, because we'll assume that Alice and Bob are in a co-moving frame. So it's well defined to separate out the position and time from each other. And a lot of subtleties with Unruh DeWitt detectors where the detector state depends on the relative motion isn't going to come into the calculation. But of course, if you start thinking of the limitations, then even if Alice and Bob are slightly moving, the subtleties of Unruh DeWitt detectors come into place. So we have the field operator, and I'm going to take it as a scalar field. So that means the detectors are effectively monopole detectors. So we have, we're going to expand it out in plane waves, e to the minus I mod k t minus k dot x plus the Hermitian conjugate divided by normalization 2 pi cubed to k absolute value. So we have a field operator like that. And then the detector has two energy levels. So the detector has two energy levels. It's very funny because in my language as a quantum optics guy, with two energy levels, I would call the detector a dipole because it oscillates between, it's an electric dipole, but in the language of Unruh DeWitt detectors, it's monopole because of the scalar field. So it's one of the interesting mismatches of language I've run into. Okay, so that's spread out. Then we have, we wind up with two levels of the detector, and so we just wind up with Pauli operators, and the Pauli operators represent, somebody's beeping. So then we have a raising and lowering of the energy level of the detector corresponding to the interaction of the field. And now to cut to the chase, I'll write down an interaction Hamiltonian. So we have an interaction Hamiltonian, and this is standard for Unruh DeWitt detectors. I'll write the Hamiltonian HI with a hat on it. I'll use hats for operators. Is the sum where nu can be A or B. That's Alice and Bob. Each one holds a detector. And then we have some coupling strength. So this corresponds to the strength that the detector is coupled to the vacuum field or to the field. And I won't go into the details. Okay, there's a lot I could say. But this will be the Knuth detector, how strong the coupling is. It's essentially a rate of exchange between if you have a particle in the field and the detector, how fast does the detector react? How fast would it go back and forth? Now we have a chi nu of t. So this is the coupling. This is the switching. So Alice and Bob are going to turn on the detector and turn off the detector. And what's going to happen with the switch is Alice and Bob are going to turn on, turn off. Bob will turn on, turn off. But it's crucial, this is what we're finding in our calculations, that, I mean, they decide in advance. So somehow they communicate with each other, agree in advance what the protocol is going to be, how long it will be on, how long off. But knowing when Alice is going to turn it on, when Bob is going to turn it on, and when they're going to turn it off, there's some decision about when these synchronization events are going to take place, and they depend on how far apart Alice and Bob are, whether they're space-like separated or time-like separated, and so on. And then when you start doing your integrals, you see all these things just happen automatically. Okay, and then we have the integral d3x of mu nu of t. So that's the, here you get an electric dipole, and that becomes your mu nu t of operator. I didn't write it down, but it's the transition operator between two energy levels described by sigma plus, sigma minus. By the way, so I'll skip, I don't have enough time to do everything, but if I skip a step and you want to know, just interrupt and I'll fill in the details. Okay. We're going to do both. So we've calculated in two ways. We have the instantaneous one, which is dangerous because of ultraviolet divergences. But we've done that one, and then we have a spatial smearing function, so the ultraviolet divergence doesn't appear. And then we've also done it for Gaussians. So, because we want to make sure our calculations aren't dependent solely on pathologies of the switching function. But this, okay. And there are certain properties the switching function should satisfy in order to be well behaved. Okay, then we have this is the dipole, electric dipole transition. This F nu of x minus x nu. So this would be the position of the detector, and this is a spatial smearing function. Okay, so this just says that the detector is not a point, it's got a size, and so in the Unruh-DeWitt description, it's a particle. If you then start thinking about it having some transition, it's natural to think of it as an atom, so you can think of this as having a scale like the Bohr radius, if you just think of hydrogen atoms as detectors. But these kinds of things become important in the detailed calculations. And finally, we have the phi hat of xt. So this interaction Hamiltonian is really just saying that you have an energy transition in your detector, which is driven in a linear, it's linearly coupled to the field in this model. There's a smearing function over the detector, and so on and so forth, and so that's what's going to happen. And then Alice is in her part of the universe, Bob is in his part of the universe. They're turning on their detectors. So Alice will turn on her detector. It will interact with the field for some time. She turns it on. Bob has his switching function. He turns it on, turns it off, and each detector interferes with the vacuum. You hope it becomes entangled, and then, as I said, Alice and Bob will meet to determine their entanglement. Okay, or they could do all kinds of great things like teleport or whatever. All right, so now it turns out, so I got zillions of calculations here, and I'm not going to write them all down. But what happens here is, okay, so we have that expression. I can do Fourier transforms on it, make it look nicer, which we kind of do. But the next step I want to get to is, given the interaction Hamiltonian, we can now have an evolution in the interaction picture. And here, it's like a UI operator. I won't put hats on unitary operators, but other operators I will. So we have our UI, and our UI can be written approximately in a perturbation theory by 1 minus, and then we have integral minus infinity to infinity dt h hat I of t. And this is the first order perturbation theory term. So this is, I'll just call that u1 sub I. And then down here, we'll then subtract the double integral. It's just kind of basic. dt prime h hat I of t h hat I of t prime. Okay. Is there a question? No? All right. So then we have that one. This is our UI2 term, and then we would do like a minus plus dot 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 to take into account. And then the expansion is in terms of lambda nu. Lambda nu, remember, is the coupling strength. So it turns out that if you have a detector, if I have the detector and I have like two energy levels, and this separation is omega nu for the Knuth detector. I'm not sure how many of you still see h bar anymore. Most of you probably set it to be 1, but I'm still old-fashioned. So I'm going to put an h bar in to keep track of energies. So I've got my lambda nu, and as long as the lambda nu is much smaller than the transition rate, the perturbation expansion will be believed to be valid. So it should be good. And then what happens, and I'm doing this carefully, it turns out we found that in the early work there's a mistake. So I'll show you what we're doing, and then we uncovered a mistake in the literature, which is not critical for assessing entanglement, but for correction terms, the mistake is crucial. So I'll tell you what we do, and then I'll just tell you what the mistake is. I'm sorry, I don't want to criticize anybody, so I have to tell you the mistake, but But I'm sure they're great people who just didn't check one thing. Okay, so now the next thing we want to do is to deal with the state of the system. So for the state of the system, we write down the density matrix, state rho. Anybody not comfortable with rho being a state? So the state is a trace class bounded compact operator in the Banach space. The norm is the trace norm, and so we just deal with it. So all the states are like that. The reason I'm emphasizing it is because the mistake in the literature happens, this goes back to the work by Resnick and colleagues, is they like to work with the wave function or the amplitude. And when they did it, the calculations are a lot more complicated than dealing with this density matrix. And once they got up to fourth order perturbation theory, they had some of the terms and not others. And the way we're doing the calculation with our rows is you don't have to move all these vectors in Hilbert space around. It's better to deal with the operator. Okay, so we'll deal with the state rho, and then the state rho can be expanded as rho is rho naught plus rho first order. Oh, sorry, did I get that wrong? Plus a rho 2. That's the initial state. Rho 2 plus the order of lambda cubed. Okay, so we now have these expressions. I'll just write down what they are. So the rho 1 is equal to U1 rho naught plus rho naught U1. And then we have our U2 term, which we get out of, rho naught 1, sorry, this is U1 dagger. This is U2 rho naught plus rho naught U2. So the idea is that this rho represents the state of the field plus 2 detectors. So often in quantum information, we would call this a tripartite state. Of course, the field state is very non-local, but it's just a three-party state in there. And then what we need to do eventually is we want rho AB. So this is the shared state between Alice and Bob, and this is obtained by doing a trace over the field of this rho evaluated after some time. So Alice and Bob are going to collaborate. They'll turn on their detectors, turn them off. In the end, they'll get a state rho. But when they turn on their detectors and turn them off, if they are lucky, they'll have entanglement between each of their detectors and the field. And then the goal of this protocol is to ignore the field, whatever it is, throw it away. Mathematically, that's a partial trace of the state to get that result. So that's the plan. And then, okay, we're going to start with, where's the brush? It's probably right in front of me. Okay, that's right. I think I'm going to keep, oh, where? No, I don't. That's a brush? Oh, okay, it looked hollow. So now the problem, okay, so the first thing we have to decide, and to me this is even a problem in itself, but we need an initial state. Okay, so we assume that the universe is created in such a way that it gives us the vacuum, and then we'll have 2 detectors. So we have, if we take the state to be 0 GG, so this will be, this is the field state. This is for detector A. This is for detector B. G is the ground state. Okay, so we assume that the universe is prepared in the ground state, and Alice and Bob have both got the capability of putting their detectors down in the ground state to begin with. Okay, so somehow if it had any energy, they wait long enough, it dissipates. It's in a cryostat, so it's very cold. So then the rho naught is simply the state given by this ket and this bra. So that's our initial state. And then we have an excited state for the detector, that's E, and the excited state and the field excited states, which we heard about in the previous talk with the number states, so the field excited states are given by number states, and they're labeled by momentum. So we have a continuum of momentum states, we're integrating over them, and so there's some number to given momentum, but in the ground state, there's no support over those except the complete vacuum. Okay, then, all right, so I've said that rho AB is the trace. Okay, now what I'm going to do is just to introduce some integrals, and they're important, you know. Okay, so I have to, all right, so now what I want to do, so this is going to feel like an undergraduate calculus class. I hope that's okay. Sometimes we need calculus. Okay, then what I'm going to do is to introduce some integrals and talk about them. So one of them is I'm going to write as I nu of k. It's got no meaning at the moment, I'll tell you. And this is going to be given by lambda nu e to the minus I k dot x nu over root 2 mod k. And then we'll do the integral minus infinity to infinity dt chi nu of t e to the I omega nu plus mod k t. Hope that's readable. And then we multiply it by f tilde of k. Okay, so let me just explain for the moment why this is relevant. This I nu of k is simply an integral that will depend on the particular mode of the universe that we care about, some momentum. And then that's the coupling. That's just a plane wave, normalization factor. And then this is essentially a Fourier transform, except we have a weighting over the smearing function. So our detector is spatially localized. So we convert by a Fourier transform to the momentum domain. And then we take the transform of the switching function. So the switching function is, of course, physically what Alice or Bob would do, turn it on and off. But it doesn't come directly into the expressions. What comes in is some sort of a transform of that. If f of k were taken out, so if you have a point detector, this would be flat, and it would just be the Fourier transform of the switching function multiplied by the corresponding plane wave. Does that make sense? That's the transition energy of the Unruh DeWitt detector, 2 energy levels. Okay, so that one becomes important. Now there's another one. Okay, and there are 2 of them, right? Because nu can correspond to Alice and Bob. Now I'm going to introduce the j. Okay, so this will be the last long integral I write, but I need to tell you about it. So this is lambda squared. Let's just pretend that the coupling strength of the 2 Unruh DeWitt detectors doesn't matter if it's Alice or Bob. Then we're going to integrate from minus infinity to infinity over t and over dt prime. This is a double integral. So essentially what's happening is this quantity only it's the local thing, right? This will characterize Alice's interaction with the field or Bob's, not jointly. This is a double integral. So this double integral is extremely important because this will capture all the non-local effects for the interaction of the detectors. So any entanglement is going to be buried in this. So this integral is crucial to understand how scaling this protocol would work. Okay, now we take a product, chi a of t, chi b of t prime. So you see this term, it's the product of the switching functions. Remember what I said, that it's very important that Alice and Bob know when to turn detectors on and off. So that product is going to represent whether, if Alice turns her detector on and off before Bob even turns his on, you're going to get a 0. You see? So you want to do things so that you maximize the overlap of the detectors. That optimization becomes very important to get this to work. Then we take times e to the I, and I don't think you want me to write everything down. So it's just going to be something like that with the 2. So it's like this term, but doubled because we have 2 detectors. And then we, I need to put, let's see, do I need that? Okay, then there's a conjugate, right? So I'll add on a complex conjugate term, and then we'll multiply that by f squared of k tilde, so the Fourier transform of the spatially localized detector, normalized to 2 mod k, and we multiply that by the plane wave, e to the I k dot xa minus xb. That's it. So that's this calculus exercise. So then you see what's going on here. This one you understand then is some transform of your switching function, and this is a transform of the joint switching that characterizes how well Alice and Bob have synchronized their detectors. Which one? Yeah, k is out here. Oh, yeah. You're right. Okay, yeah. So that's, he stated the obvious very elegantly, and I'd overlooked it. Yeah, this comes out. So I was saying a story about how it's like a Fourier transform, but it's precisely a Fourier transform of the switch.
So when you write the formula for J,
yeah.
these guys would be describing a situation where the detectors are always on?
Yes, but it won't work. You're right. So it could be done, but then the question is, because we want to see the entanglement. So now I got to, okay, so we have those quantities. Oh, yeah, he's right too. You can't both be right. Yeah, Fourier transform will give a k-dependent quantity sitting. Okay, you're both right. That's it's good news. Okay, now I want to define just two more quantities that are easy to write down. So first of all, I'm going to write, I'll write a calligraphic I, and I'll put a nu and nu prime. So this can be defined over like Alice and Bob, Alice and Alice, Bob or Bob. Okay, and then, so we have that quantity there, and then this is just going to be an integral of d3k of I nu star, gotta erase things. Okay, so we have I nu star of k I nu prime. See, after I give this talk a few times, I won't have to keep checking, I'll remember, but I nu prime k prime. Okay, so this becomes, it's kind of like a power density or autocorrelation or something like that coming in. So we don't need this quantity directly. When the detector collects it, it collects the energy. So we're just converting, in a sense, of spectral densities and integration. So because we just care how much energy the detectors are going to get, the energy is what causes the state to go from ground to excited. So that doesn't matter. This matters. And then we have a J, which I'll write as a calligraphic J, and that's equal to the integral d3k mod j of k squared. So this is the quantity that matters in terms of getting the entanglement. This one will cause Alice's detector to get excited or de-excite. So this will tell how much energy goes into each of Alice's and Bob's detectors. And this quantity is going to tell us something about the joint excitation. So the entanglement is, and I'll show you mathematically in a moment, but the entanglement is kind of buried in a difference between how much you get jointly minus how much you can do separably. So the separability lives in there, the jointness lives in there, and the difference captures how entangled the detectors will be.
Shouldn't that k prime also be indicated in the first part?
Oh, yeah, correct. Yeah. Oh, sorry, no. Yeah, it should have been, but the prime is wrong. Yeah, okay. Then we calculate. Okay, so then there's lots of calculations. So about 5 pages of calculations in 2-column physical review type format. So lots of stuff that goes in. It's probably easy to do, but we just don't see it. So you calculate the whole thing, which I don't do for you, and then eventually we get a state. So eventually we obtain a state, that rho, good chalk. Okay, so eventually, after all that, we obtain rho AB. So let me write down what the rho AB is. It's a 4 by 4 matrix. So we get 1 minus I A A minus I, that's the I there, BB, and then 0, 0, I, AB. And then here we get 0, that should be a star, 0, I, maybe I'll hold this, I, BB, and then minus J, 0, boom. Okay, next one, 0, I, A, B, minus J star 0, minus J, I, A, 0, 0, 0. So that's what we get. You can kind of see what's going on. That, remember what I said, this captures separable properties of the detectors. So they live out here. Then over here, the J's come in as off-diagonal elements. So they're crucial. You also have the IAB is off-diagonal, and the J's are off-diagonal. So you can get the sense that there's some sort of a coherence between Alice and Bob emerging out of the IAB and the J. And then these terms just capture independently what they get in the detectors. So this is a 2 by 2 matrix, and I'll tell you what the basis is. So the basis is, make sure I get the right order, GG, yeah. So it's the GG, GE, EG, EE, and then we would have the opposite here, right? The bra, et cetera. So that matrix is expanded in the basis of, we can now think of the detectors like qubits, quantum bits. Each one is a 2-level system with a ground and excited state. And so this is just telling us those matrix elements. So now we have a complete description. It's a 2-qubit state in quantum information language. And it's described entirely in terms of those quantities. I mentioned there was, so now in Resnick's stuff, brilliant stuff, great, wonderful, but the mistake, we have a 0 over there, they don't have it. So in their calculation, they don't actually get the same matrix. And the reason is that when they did the 4th order perturbation theory that you need to get it, if you work with density matrix, 2nd order is enough. But if you start working with wave functions, psi, then you have to go to 4th order. There's a lot of terms. They kept some and threw some away. And you could tell there's a mistake because the trace of the density matrix has to be 1, and their trace is not 1. So it's easy to check. But the good news is, even though they made that mistake, the error doesn't go into the calculation of entanglement. So their entanglement calculations are valid. So being sloppy with the 4th order amplitude terms didn't change the result that they were advertising. So the end result of their paper looks correct to us, but the density matrix is not. The fact that the density matrix is different actually matters because the calculation of the entanglement in the system directly comes out of this. So we want to get that density matrix right. Okay, so now we have a system that it's a 4 by 4 matrix for 2 2-level systems. And it's got that non-local coherence, and so that's code for saying it's entangled. So now we have to calculate what the entanglement is. And there's many ways to do entanglement of 2-qubit systems, and they're all equivalent. So it doesn't actually matter which one you pick to determine the entanglement, but I'll get into something more important in a moment. Okay. No what?
The statement is there's no probability for both the detectors to be excited simultaneously in this
Yeah.
discussion Hamiltonian?
In ours, yeah. So that one.
Why would that happen?
I don't know. It's a good question. I don't know why it's a 0. It's very funny. I mean, you're asking a key question that you look in literature, and the one that's published years ago has a non-zero there, and we find a 0. And we verify, so we were surprised too. We verify trace as 1. I don't know the answer. It's one of the things that I don't know yet. So, but if you see or anybody sees, let me know. I'll write that in the paper and put your name down in the acknowledgement section. It's a career move, you know. Pardon me?
Because of the 0, is the positivity still preserved? Is it still positive because the corners
so let me write down the negativity, and I'm going to claim it is under some conditions. And if you're right, then it can't be entangled, correct?
No, and the state itself must be positive, right?
Sorry, state's positive.
The state has to be positive.
Yes.
But then if you
Oh, so you're saying I got a mistake in the density matrix that doesn't give.
That's okay, right? It should be 1, 0, 0, 0. Initially it started off
no,
with
but
1,
if
0,
you take the top corner and this is 0, and then if you minus this in the modulus of tilde I square, right? So that gives the negative.
Well, okay. No, he's good at this kind of thing. He's wired for it. I know this. So that's why, like, if I give the result and he questions it, I'm trust him more than myself. But let me go ahead, and I'm going to write down the negativity, and we do a partial transpose, and then let's do it. But you run in parallel what's going on and tell me, because if you're right, then I mean, actually, I hope you're right, because if you're right, then it can't work, right? And you know, bad news is interesting. So let's see. Okay, so now. Oh, did I make a mistake? So let me. Oh, did I write it down wrong? That's probably transcription error. Sorry, yeah, this is. Oh, so you know what I did? That's the partial transpose. So let me just fix it. I jumped ahead. Then it's fine. He's right, because I wrote the wrong matrix. That's really, really impressive. Okay, how many of you can do partial transpose in your head? That's, you know. Okay, so what Ujjwal realized is the following, that the correct one is rho AB is 1 minus IAA minus IBB, 0, 0. That's the J term down here, minus J. Then we get IBB, IAA, 0. Okay, then we have IBB, IAB star, IAB, minus J star over there, 0, 0, 0, 0, 0, 0. Okay, that's the correct state. Then this is the one that we get. This is the rho AB under an identity cross a transpose. So we do, this is known as a partial transpose in quantum information literature, and we get that. And so the fact, then you agree, right? This is the state, and then when you do the partial transpose, then you want to see if positivity fails. Okay. Oh, well, when you do, so you know negativity and log negativity and these things, have you heard? Or no? Okay. Do you want to say? He wants to know why we do a partial transpose. So you've done more of them than I have. I'm trying to get discussions, so you don't want to say? So what happens? I'm trying to remember the statement of the Paredes-Hordetsky criterion.
Yeah, so for separable states, if you do a partial transposition, the state remains a state. But for entangled states, then if you do a partial transpose, the state may not remain a state. And this is a 2x2 system. In that case, it is necessary and sufficient. So for all entangled states in 2x2, partial transpose will create one negative eigenvalue for sure. So that helps you to quantize entanglement for 2x2 systems.
So that's clear. So it's that's the Paredes-Hordetsky criterion, right? Yeah. So so what Ujjwal said, it's correct that you do a partial transpose, and there's a necessary and sufficient condition that if the partial transpose has a negative eigenvalue, that guarantees entanglement. If not, it guarantees separability. So 2-qubit systems are very special in that way. So then all we have to do is determine the criteria when an eigenvalue goes negative, and then we know we got entanglement.
So can I ask you once more? I know you said you don't know the answer, but I'm just trying to understand still. So you have two detectors which have arbitrary switching on and off functions, and arbitrary, they have independent spatial profiles.
Yes.
And yet you say that there's no chance that they can be excited simultaneously. Like I measure something and I find a plus here, there's no way the other person will ever find a plus. That somehow, even though the detectors basically have independent profiles in any
Well, okay. So
I
getting,
switched on one at an early time and
no, you,
one at the light cone later.
I think you hit the nail on the head. Okay, so to get to that step, I've already started to assume, I didn't assume identical switching functions, but we get to the point where we assume identical F. I've dropped the new index there. So the detectors are identical in every way, except Alice and Bob still have freedom to choose the switching functions. But I don't know why it's a 0. But it's, I mean, the fact that you're disturbed by it is good, because it seems weird. That's why, so I don't know the answer, but that's why I'm reassuring you we went back and checked the traces of density matrices to high order. Okay. Now, so now you know the partial transpose. Oh, sorry.
Other than the one, every entity there is order lambda squared.
I think so. I erased the IAB, but that's order lambda. That's order, yeah, order lambda
So if I
squared.
had two independent excitations, would that be order lambda before?
Yeah, but that's, oh, you're saying that's why it vanishes. Okay, okay. Well, actually, that's okay. It's good giving a talk on half-finished work. I think that makes sense. So the argument that Rob is giving is that the reason this is vanishing is it's a perturbation theory. So if these are all lambda squared and then you want to couple and get both detected, that would be, yeah. Okay. You get an acknowledgement. Okay. So, all right, yeah.
So maybe what those guys did the fourth order correlation theory was okay, but did they have lambda in the fourth there?
No, it's incorrect. You can look at the papers and compare. I mean, either, they can't both be. We have two results. They don't agree. At least one is incorrect, maybe both. That's the logic. Okay, so now, what we're going to do is we can calculate the negativity. So negativity, we heard about it. So the negativity is the sum of negative eigenvalues of the partial transpose. It's not parity time, partial transpose of rho, okay? And then let's just call that n. N is the negativity. So when we calculate that from the 4x4 matrix, we get n equals minus a half IAA plus IBB minus the square root. And then we take the difference, IAA minus IBB squared plus 4J squared. Okay, and then we'll add, I'm dropping the orders, but plus the order lambda to the 4. Okay, so that's the negativity. That's the sum of the negative eigenvalues of the partial transpose. And so, and then now in Resnick's work, they discuss the case that, so there's a case that IAA is approximately IBB, and in that case, then we get that the negativity is minus a half, the sum of the two. It's, I should write it like this, it's J minus I. So if we think of this as an I term, that's what we get. Okay, so remember what I said early on? I said you can kind of see that the entanglement, all the correlations are locked in there, the classical part is locked in there. So if you make that assumption, then you can see that the negativity is J minus I, so there's a very nice interpretation. So what I was hinting at with all those integrals is very clear in that expression. Okay, but we don't do that in our calculation. So we don't want to make that assumption because we're worried about the protocol, noise in the system, all these kinds of things that will damage it. So we stick with that negativity expression. Okay, then, so now you get the idea that you just plug everything in and you try to integrate. I got very long expressions I don't want to write down, so I'm going to kind of go to the punchline for it. We deal with two different cases. So we have the cases. There's the sudden switching, and there's the Gaussian. switching. Okay, so this would be, in one case, your chi of t would look like it would go on and off. In this case, your chi of t would come on and off like a Gaussian. Okay, so it's slowly on and slowly off. Both of these have mathematical issues. Anindya was worried about the switching function before. So in this one, you have to worry about a UV divergence. But we argue that that's eliminated by the smearing function. And the other one you have to worry about here is the long tails. So a Gaussian has infinite extent, and it means that Alice's detector and Bob's overlap. So then you just have to be careful that the entanglement you get, if you get it, is not mathematically due to overlapping detectors. But you know, if you're out, our calculations we do from 50 sigma to 1,000 sigma spread. So with the Alice and Bob, you know, like the spread would be, sigma would be the spread of the wave function. So if an atom is a Bohr radius and you assume that Alice and Bob are separated, you know, even on the scale of microns, the probability of getting an overlap, so the overlap contributing to the signal is of the order of e to the minus 10 to the power 6 or something like that. So you're going to be waiting longer than the lifetime of the universe for any events to show up due to that overlap. So both are fine. So we do the calculations in both cases to just check it. And then, now the next thing that I want to say to you is once we do the integrals, there are so Alice and Bob turn on and off detectors. Okay, so now there's 3 cases that we consider, 1, 2, and 3. And the first case is that detector nu is off before nu prime is on. Okay, so this says Alice turns on her detector, turns it off before Bob turns his on, or vice versa. So this is the no mutual support. Remember that the J vector had the product of chi's? So if this happens, there's no entanglement in that case, okay, because they have to have their detectors on at the same time. The second case is, where'd it go? Oh, I wrote it wrong. I won't say. So the second case I don't care about, but I wrote it incorrectly there. But there's no entanglement. So this is whatever. I'll leave that case. I can't remember. I don't want to waste time.
Before means the time like set.
Pardon me?
Before means the time like set.
We're just doing it in a simple case. So Alice, all the time difference, you know, the time zone change because of relativity is all taken into account. So we just write it in common T units, and Alice and Bob know their relative reference frames and correct for it. So then we have overlapping chi's. And in that case, then the idea is that we can get entanglement. Okay, so we then calculated, it turns out that we have intervals, right? So you can imagine that in this case, you care about the overlap. Alice turns on her detector, Bob turns on his, how much they overlap. Now, it's an optimization problem. They want to overlap it long enough to get as much entanglement into that 4x4 matrix as possible. So you allow them to do that. Now, the next part of the calculation, when you do that, is, so you want overlap the chi's optimally. And we've done plots of these things. So what happens is with Alice and Bob, and they start to do it, we'll start to see, like, you know, the entanglement, the negativity. And then on this axis, we might have a separation, right? So this is the separation between Alice and Bob. And then once we start to do the plots, we might see some function which looks like this, and we have a light cone over here. And so what we see generically in every case is that the amount of negativity is very sensitive to the separation between Alice and Bob. And So it turns out that when we start to optimize and see how long it has to be on. So, Alice has her detector. So there's Alice, turns on a detector. Bob turns on his detector. Then, so they're going to overlap in some optimal way. And then there's like an overlap function. And the time scale for this turns out to be the time it takes for light to go from Alice to Bob. So that's the natural scale in the system. So there needs to be, that's what we're finding in our simulations, is that that natural time scale starts to emerge once we optimize the protocol. Okay, so Alice and Bob have to optimize that. I don't have time to go into that, but I'm going to tell you the next issue. And so the next issue is, so if they optimize the overlap to increase negativity, suppose they do it. But the problem is, having entanglement in itself is not useful in quantum information. If I promise you entanglement, so in entanglement we have Bell states. I don't know if people know this, but Bell states. So if I write a Bell state, I've got the phi plus minus states, the psi plus minus states. I can't remember these. 1 over root 2, 1 over root 2, and then this is going to be, let's see, psi minus is a singlet. So I get 0, 1 minus 1, 0, qubit state. So I get a plus, and then here I get something like 0, 0, plus or minus 1, 1. So those are the four this represents a good it represents a good basis for the two-component system. Now, each one of these states, if I give you, so you get the state phi plus, and you know it's the state phi plus, then you can then you can use it. So if Alice and Bob can do the protocol and know it's the state phi plus that emerges out of the protocol, they can use the state phi plus to do teleportation, dense coding, teleport gates in a quantum computer, whatever they want. But the question is, even when they optimize the negativity, do they know which state they got? So the next calculation we're doing is we want to then consider, say, the phi plus component of the row. So the idea is that they think, they do the calculation. Alice and Bob are really smart. They know how the universe behaves. And they say, okay, if this works, we know we got the phi plus state. But what happens over here is when you get the flatness, when we start doing the simulations, instead of being somewhat flat, which Bell state they get is very sensitive to the protocol. So, so it's not clear that the entanglement that can be harvested from the vacuum would be useful in any sense. It goes even further, the entropy principle. So Jaynes's formulation of the entropy principle, if you don't know what state you got, then you have to average. So if I promise you that I'm going to deliver you a Bell state, but I don't tell you which one, then, so if you're ignorant about which Bell state, then you would say, I don't tell you which one, then you have the state phi plus plus phi minus plus psi plus psi minus, close that, normalized by a quarter, that's equal to the identity. So if I promise you I'm going to give you an entangled state, but I don't tell you what it is, and then you follow Jaynes's principle, maximum entropy, you have no choice but to write it as an equal mixture of all the Bell states, and that's an identity, and that's useless. Identity means you know nothing about your state. So it becomes important, Alice and Bob, to know which is the state they're going to harvest out of the entanglement of the universe. And like I said, so if this were somewhat smooth, really flat and smooth, then if Alice and Bob have errors, they know which one they're getting. But if the state would change, say, on a Planck scale, they got no hope of ever knowing that. And that's part of what Eduardo and I are still calculating. Okay, so I'm going to wrap up in a moment. Okay, so that's the second thing that we've got results on. Okay, the final thing I wanted to tell you, and it's an area I like a lot. So there's an area known as quantum reference frames. Okay, we often call this frameness. So what's happened in the field in quantum information is we're starting to get aware that entanglement is just one of a multitude of resources needed to do things. So the idea is that, if Alice and Bob want to do a teleportation protocol, they have to know each other's frame of reference, so they could do a Lorentz transformation or whatever, but they need all those parameters. The parameters in these transformations are continuous, so they're represented by real numbers, and you can't know a real number perfectly. So then you can start imagining protocols where Alice and Bob know how far apart they are from each other. You have to figure out how much, so then they have the entanglement, but the frameness, the resource, etc. And then it turns out that you can start, okay, so let me tell you, in teleportation, the idea is that if you want to send a quantum, a qubit through a classical channel, the cost is one entangled qubit, like that 5+ state, plus 2 bits. So we're kind of at a point where we can think about all these quantum information protocols by imagining there's a supplier. So suppose that I open up a shop and I'm selling you 5+ states. Then you can buy them and you could do teleportation, dense coding, teleport gates in a quantum computer, whatever. It's like a currency. It's fungible. So you can trade it. One day we could have entangled qubit exchanges like Bitcoin, but you'll make more money. So there's a cost to it. Here, for frameness, there's also a cost. Now, where this becomes important is for Alice and Bob, well, A and B, they need to synchronize. Let's understand what they need to do to synchronize. In order to synchronize, they have to go through a protocol to know how far apart they were. I wrote down over here the separation. But how do Alice and Bob know what the separation is between them? And so the answer is that they'll send qubits. They might send signals and see how long they take. But then there has to be a clock. And then the clock will also carry some quantum resource. So somehow the universe can't just have an entangled ground state, but the universe also has to have a clock that's sufficiently large that Alice and Bob can tap into to be able to conduct the protocol. If you want to believe in a classical universe, it's fine. If the universe has a quantum field and there are classical objects like pulsars that you can use to synchronize, it's great. But otherwise, what we can do is start looking at, instead of saying, well, the sensitivity is exponential or something, we can start building the clock in as a quantum object. We went to all the work to trace out the field, but once you get the clock there, we'll have the field, we'll have Alice, we'll have Bob, and we'll have a clock. And once you start dealing with the clock and tracing over, these things start to become problematic. So this is kind of where we're at, is trying to figure out in principle what would happen. And it turns out that a clock in precision scales, so clock time undergoes a random walk. Every experimentalists know this. The laser, if you turn on a laser, the laser frequency undergoes a quantum walk. But this is even an in-principle thing. If you tried to build an ideal clock in the universe, and then if you don't use it, it will always tell the correct time, but you'll never see it. But if you start to interact, it's the Newtonian principle. Every action has an equal and opposite reaction. So the mere fact that you lose the clock gives it kicks and causes it to walk in some fashion. If you don't use up entanglement to keep your clock synchronized, then the wander will go with the inverse square root of the number of particles in the clock. If you make use of entanglement, then you can bring it to 1 over the number of particles in the clock. So depending on whether we have entanglement that we use for synchronization or not, we can get quadratically different scaling principles on precision. But that precision puts error bars on this. So the position, if you take Alice and Bob, are separated by XA minus XB. There's a delta on this, the standard deviation, and this will relate to the imprecision of the clock. So that's kind of where things are at the moment. So I'm going to just summarize by saying that, okay, so just to take you through in case you missed any step along the way, the idea is that, so we're taking this protocol, which, very clever protocol, Benny Resnick and colleagues suggested 10 years ago. The idea is theoretically there exists entanglement in the ground state of the universe. No question about that. We do the calculations. We find that. Then the problem is, first of all, is the entanglement useful? Because there are 4 different 2-qubit entangled states. So Alice and Bob, Alice and Bob might harvest entanglement, but if they don't know what it is, then it's not operational entanglement. It's completely useless in my way of thinking. So it's just a mathematical exercise. So they have to know what they're getting. And then what they're getting is going to sensibly depend on synchronization. And synchronization, on a fundamental level, can involve questions about the clock and where it comes from and how it's used. And then the idea is that what we find in our calculations, roughly, is extreme sensitivity. There's a time scale for the protocol, which has to do with the time it takes for light to go from Alice and Bob. And then you start to ask, what is the precision required? And anyway, all our calculations are showing that that there's like a hypersensitivity to the clock imprecision in order to harvest the entanglement and get useful states. But we don't have that result ready yet. Done.
How much does this depend on the fact that you really had the vacuum exactly to do the calculation in? What if the universe happened to be in a slightly excited state with some lumps of matter?
But that's, I mean, so of course, I could tell you mathematically, we had a 4x4 matrix, right? Traced out. Well, okay, it'll still be 4x4, but the...
But these numbers will change.
Absolutely, yeah. I don't know what would happen. We don't know. Could be bad. But I know what you're saying. You're saying, in addition to the clock, what if the temperature of the universe is not absolute zero? How sensitive would it be to that? And that's another factor to look at.
Okay, let's thank Barry for a very interesting talk.